Okay. So my name is Julia Layne, and I am a software developer here in Tulsa. My day-to-day job is actually in Java and Groovy, but I've been getting into data science more, so I've been playing around with Python a lot. So my talk today is PyPy. We're calculating pi in Python and trying to make it faster with PyPy. It is as ridiculous as it sounds. So we're gonna see how many times I can say pi. If you are in your job or in a real program trying to do this, you have this really boring solution, which is the way that you should actually do it if you are trying to put this into production. So NumPy has a numpy.py, and then there's a math library that's going to have pi. So both of those are just like baked in, use them, and get on with your life. But we don't want to do that. We want to actually calculate pi. So the first way I'm going to do it is with no library. So with just vanilla Python, we are going to use the Leibniz series in order to calculate pi. And then I'm going to use just a little bit of library. So still avoiding those libraries with those lame pi variables we could just use. And we're going to do the Nilakantha series, and we're going to be using the decimal libraries just for the sake of accuracy. And then we're going to talk a little bit about how these are a little bit slow, and then get into our process improvements. So let's go over the implementations. So this is the Leibniz Formula for pi. So this takes the process of starting at 4 and then basically slowly decrementing it until it reaches pi. So you'll see some patterns in this series. So at the top of every one of these fractions is 4. So that's always going to be our numerator. And then you see it oscillating. So it's going between negative and positive. So we also need that oscillation in our loop. And then lastly, the denominators are all odd numbers. So we need to make sure that we are going through every odd number. So the code for this looks like this. So K is that denominator that we were talking about. So we're starting at 1. And then that S is going to be our sum. So that's the sum of pi that we're getting to. So we're going to loop, and each time we loop through, we're going to get an even more accurate estimation of pi. So at the top, if you're unfamiliar with loops, I have 4i in range and then 1,000,000. So this is going to take me 1,000,000 times. And then everywhere you see that I, it's whichever iteration we are on. So if our iteration, so if it's the first time through, and we have that modulo 2. So that's just checking, is it even or not? So this is figuring out that plus minus factor. So we're either going to add it or we're going to subtract it. And then at the bottom, we're going to keep up with K and keep making it positive, we're going to keep making it odd. And so with that, we can pretty handily calculate quite a few digits of pi. And at least in this one loop, it's pretty fast. So let's see what the Nilakantha formula looks like. So this looks a little bit different, but there are some similarities. So you can see that still at the top, we have that 4, and then we still have the oscillating value of adding and subtracting in order to approximate pi. So what we have in our denominator this time is this little sliding window of 3. So we'll be trying to essentially grab our iteration number and then its 2 nearest friends. So the code for that, we're pulling in this decimal package so that we can get some precision because we have that multiplication at the bottom. And usually rounding doesn't matter too much, but we're going to be rounding 1,000,000 times and more. So I want to be a little bit more precise here. So we can see here, what I've done is build a function. So this def Nilakantha, it's taking in this rep. So that's the number of times that I'm going to loop through. So this time we have op, that OP, so that's our operation. Are we adding or subtracting? So we're handling it a little different way. Before we tried it with an if and else, and this way we're just going to keep multiplying it times -1. So if you look a little bit further, you see that op times equals -1. So that's going to keep flipping that bit for us. Are we adding it or subtracting it? And then again, we're doing the loop. But this time you can see that we are doing it, we're handling it through the range itself. So we're starting at 2 because that's when our pattern here starts with 2, 3, 4. And then we are basically going to be doing it, if we're putting it 1,000,000 times, then we're giving it a range of 2,000,000. And then we are, with again, the range, instead of manually setting that K, we are saying, okay, give me a range by steps of 2. So this is doing that same functionality, but a little bit smaller. And then we have our actual result where we are storing in our variable, our what we're adding to the sum. So we're going to do that again and again and again. And we get even more digits of pi. So these are 2 different ways that you can manually through a series, and there are different series that you could implement. But what we run into, if we're using Python 3, these are just the times for the first one I went through. So this is the Leibniz series. If you increase that, it stays pretty fast for roughly up until 100 million. But then when you start bumping it up by levels of 10, so now we're going from 100 million to 1 billion, that gives us a jump. But you really see the exponential growth and how this is slowing down when we hit that 10 zeros, which is 10 billion. So then we have a huge jump in the time that it takes to calculate this. So our solution, for today at least, is to give PyPy a try. It has a just-in-time compiler. So when you write code, it might be interpreted. So it's just going to be executed exactly as is. And it might be fully compiled. So it's going to go through and completely turn your program into something that the computer understands. That's fully compiled. And this is kind of an in-between. So it is going to compile it, which runs a little bit faster because it's in computer language. But it's going to kind of be doing it as it goes on the fly, instead of trying to compile the whole thing and then go through it. So we're just going to see, hey, can we speed up this process? Because supposedly that's what PyPy is good for. So here is implementation 2 with the Leibniz series. So first, we threw that code into a py.py file, and we did a benchmark because we want to see, how long is this going to take on just Python 3. And then we're going to install PyPy. Now for this, I will say I would Google your particular operating system, and then possibly, your CPU, if that matters. And then find the specific instructions. You can download and do all the tarballing. Like if that's your jam, it's already ready for you. It's not my jam, so I found this. I'm using Brew to install it on my Mac, which is what I've been using. And then we're going to rerun this exact same program and just see how it does. So not changing any sort of code to optimize, just using a different runtime, and we'll see how it does. So here is py.py. So you can see in this one, I have done what we did before and created a function, so def Leibniz, and then I'm letting it pass some repetitions. I am importing a library time because we want to see how long it takes. So I'm getting a timestamp before we do all the work. And at the very bottom, you see a T2. And that's how I'm getting that difference between, that's how I'm getting how long it has run. So the total time is going to be however long it was at the end minus our starting time. And what we're going to do in this for loop down here now is we're doing powers of 10. So we're just doing a range of 10. So starting at 0, so 10 to the 0th power is 1. We're just going to do it once. And then we're going to keep doing that until we get to that 10 billion number. So we're going to see what the impact of that is, and hopefully it is speed. Okay, so we can see the difference. So we see Python 3 still doing its jumping thing, where suddenly at 10 billion, it's like it's hard or something. But PyPy, it does go up, but kind of negligibly, at least in comparison. So up until this 8 point, so if we looked at the rest of them, should have given you guys the graph, but take my word for it. It's pretty much the same. So kind of on those smaller scale, it's not really much of a win to use PyPy. But as you see scaling and you see that exponential growth in time, PyPy has really outperformed Python 3 when it's trying to go through that loop and calculate pi. So some PyPy caveats. So it's not going to be a magic bullet. I'm not saying like, get rid of Python 3 and always use PyPy. So for one thing, I think is probably the most important thing, that it's not going to work on all computers. Like I said, installing it is going to be a little bit difficult. Might have to figure out, I think on Ubuntu specifically, it seems like there were issues, given that might have been an old article. I have linked it later. And then if you're using libraries with C, so those need to be compiled before they're used, you actually will see more of a slowdown. So we'll have a reverse effect where PyPy suddenly becomes the slower way of running it. So it's really best for long running processes, as you saw, and it's really good at pure Python. There are some other options, of course, when you're having a long running program. One of them is, of course, to spend the time to optimize code. But there are also other things like PyPy that are just different ways to run your code. CPython is one. It uses C, as you might have guessed. And then, of course, there's cloud computing. So you can put it on someone else's computer, maybe spend a little bit of money, like for a few seconds to run at one time. Really, when I was thinking about this PyPy, it was really more, is this a script that I'm going to run one time in production? And maybe I don't want to spend all this time optimizing my code. It's not really doing anything too crazy, but it is taking a long time. So maybe the fastest way is just to give PyPy a try and see if I can run it once, runs better, and then we're good. So just something to consider. I would recommend downloading it and playing around with it. And these are the links. Obviously, I will drop those into the freeCodeCamp Slack, but I'll also pass them along so the freeCodeCamp people can pass them along to you. So that's all for me.